So, happy Thursday, officially. Happy semi-snow day, late start day for those of you with small children. At least they called it last night so we could sleep in for a few minutes if we wanted to. I appreciate it when they do that. We have, let's see, some more to do for example 2 and lecture 2. There are, I think, a couple questions that I haven't talked about that are in your bridge activity that are due Monday, so I want to make sure that I hit those about alternative link functions for sure and what is and isn't allowed. So you can be working on that and you should be able to complete all of it by today. As a reminder, 3 points for effort, up to 2 more for accuracy. So if it doesn't go well, nothing you can't come back from. If it does go well, then great. And as usual, we're going to go over it as a group. And I think Vladimir wanted to take the lead on that this time. He's going to go over the answers and the
Yes.
logic for what's right and what's not right. Yep, cool. So we'll do all of that. So let's see. We have that. Homework 1 is the next thing that's due the following Monday, so about 10 days from now. If we don't get through everything that we need to for you to be able to be comfortable actually running these models and interpreting the output, then I will push it back to Wednesday. So yes, shout out to Vladimir, doing a great job. Absolutely second that. So thank you everyone for your cooperation. Should we dive back in maybe with some review, like model parameterizations and what the hell logit is and stuff like that? Yeah, okay. So back to pictures, would that be helpful? Like nonlinear? Okay. I like this one because I think it conveys to me how the differential spacing works out. So we're talking about predicting binary outcomes, right? That's what we're doing? Big picture? We got to know what and why before we can know how. So we're predicting binary outcomes. That means a column of zeros or ones in your data. And so that can indicate a lot of things. It can be having an event versus not an event, like a finished dissertation versus unfinished. It could be something like in your first homework, getting a job offer or not, which is the thing you're going to be predicting from numbers of papers, numbers of posters, and level of quantitative training. So I simulated the data to make the story fairly clear, but I'll spoil alert for you. Quantitative training is good. Okay. That's going to increase your logit of getting a job. But the reason we use logits, why? What are they for? And feel free to talk or type. I am eagerly watching the chat. Binary to continuous, yes. So we're not transforming the data, right? We are not doing anything to the column of zeros and ones. We are feeding them into the software with instructions to use a logit link function, which changes the outcome that we're predicting into something continuous. Yes, so we need that because what we're secretly predicting in terms of the zeros and ones is the probability of getting a 1 rather than a 0. That's what the model is focusing on. So logits take that predicted probability and turn it into something that is truly continuous. That way, when you have a regression slope, it can keep going and going and going and predicting logit, 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 logit. But when you back translate that into probability, the probabilities stay between their boundaries of 0 and 1 where they're supposed to be. So if I wanted to say back translate in a paper, what would the formal phrasing be for that? Inverse is the first word.
Reverse link.
Yep, inverse link. Yep. Inverse link. You will hear me say unlogit or back translate as synonyms for that, because that's the way that I think about it. So the logit is the continuous metric that the model is trying to predict. We will back translate those predicted logits into predicted probabilities using the inverse link function. So this shows the mapping then of probability to logits. And the big thing that I want you to notice is that equal changes in predicted logits do not correspond to equal changes in the amount of predicted probability. The changes get shorter and shorter and smaller the closer you get to the boundaries. So a predictor's slope is going to be most important, most effective towards the middle of the probability distribution rather than the boundaries. And yes, a friendly reminder that log is natural log. So it's ln in Excel, for instance. In some software packages, it's log. Sometimes it's ln. You just kind of got to look to see what the documentation is. But it is the natural log, not log base 10 or anything else that you might have come across with. That is true in statistics universally. like log 10 or log 2, or that never shows up in anything. It's always natural log. So the model then that we're using, oh, wait, let me back up one more time. So what's the other thing that we're doing differently beyond the link function relative to what you're used to normally? There's a hint. What are we doing differently in addition to the link function relative to what you are used to normally in predicting a continuous outcome?
Bernoulli?
Say it again.
Is it the Bernoulli or
Yeah,
distribution?
we're switching out the conditional distribution to something that's not normal, because binary data are never going to have a normal distribution. They can't. So we are switching it out to a two-choice distribution, zeros or ones, which is Bernoulli. And that distribution then implies that we don't need to separately estimate variance. We have, this is slide 10 here, the variance of a binary variable is determined by the mean, and it's a non-constant across the predicted probabilities. So if your predicted probability is 0.5, that's the most variance the data can have around that point, and it shrinks as you get closer and closer to the boundaries. Question, is the Bernoulli distribution for the data or for the conditional mean? Great question. Data. Bernoulli is for the zeros and ones, because that's what we actually have in reality. The rest of this is sort of an elaborate fiction to justify the scaling of the model in terms of what we're going to call residual variance. But Bernoulli is for the real data. It's the conditional distribution, meaning incorporating predictors of predicted probability. So the model treats the logit as if it is normally distributed and unbounded. Close. Very close. Let me skip ahead a few slides to answer that question. So this is slide 15. I think we did this briefly once and we'll go back over it. The model assumes that the logit is distributed as a logistic distribution, which looks like normal, but it can be a little bit, squishier, depending on something called a scale factor. In binary data, the scale factor is forced to be 1 for identification. It can't be estimated separately. So it looks kind of normal-ish, but the difference between logistic and normal is the difference between logit and probit link functions that we're going to introduce today. So yes, link function to solve the problem of predicted probabilities going out of bounds. That's one step. And then switching the distribution to something that is more plausible and specific to binary data, from normal to Bernoulli. Those are the two new points. Okay. Let's do slide 12 here, talk about different versions of the model. So you will see this same model written several different ways depending on what y is. So the top one here is the logit version. So the log of the odds of the probability of a 1 is what the y is here. That is going to be abbreviated by mu in the Stata textbook. Harbin, I can't remember the author's names, but it's the one that's recommended. If you don't buy it, that's fine, but I think they have a lot of good explanations, and I use it for a lot of what I'm doing here. So they abbreviate that as mu in this case, like the y in logits. And then our linear predictor is this part, the fixed intercept and slopes, works the same way as usual. So this is nice in that I know exactly what to do with the intercept. It's the expected logit when the predictors are 0. Each of the fixed slopes is the change in the logit of y for a 1 unit change in x. So we have the familiar interpretations, all is well and good. H and H, yeah. Hardin is one, and I forget the other one, but it's on the syllabus. We'll find it someday. So I like this, but the problem is then, what the hell is a logit? Like if I tell you, oh, you have a predicted logit of 2, like, is that good? Well, if having a 1 for your outcome is good, then I'd say it is, because a logit of 2 means that you're closer to 1 than you are to 0, because the neutral point in logits is 0, corresponds to a probability of 50-50. So the problem with this model is not on the right side, it's the left side. Then we have this intermediate thing that only shows up in categorical data. It doesn't have an analog in the rest of the outcomes we'll be looking at, thank goodness, because I hate it. We have odds. So if you strip off the log part, then essentially what happens is the linear predictor part gets exponentiated. So it's e to whatever the sum is that's in this parentheses there as an exponent. And if you distribute the exp, then you end up multiplying these things together, and that breaks my brain. But odds then just gives you the relative difference here with respect to probability of 1 versus 0. And then we get down to the last one, which is the inverse link version, which is directly predicting probability. So if you write the model this way, then people abbreviate it as P for the probability of a 1 for this individual. And it's e to the model over 1 plus e to the model, where the model is in logits. So at this point, I can't talk about any of these betas using familiar one change in this leads to this language. It doesn't work. The whole thing just sort of falls apart. But I can back translate the predicted logits into predicted probabilities by using this formula. And so this is one that I had suggested just trying to commit to memory. It's e to the logit over 1 plus e to the logit. That's what we got here. And if you want to do less typing, here is an equivalent version where we put a -1 in the denominator, and that simplifies it so you don't have a numerator at that point, and it works out to be the same thing. So this is logistic regression. We are translating the probability of 1 into a more continuous metric in logits so that we can have slopes and intercepts that work the same way as usual in predicting logits that go on forever. We back translate it into probabilities that stay within their boundaries. Okay, questions so far? Or any that you want to hear again or more slowly or differently? No, everyone's quiet today. Still recording. Got to make sure I check on that. All right, then we'll move on. So order of operations of these things, this is a tricky topic, and we'll go over it as many times as it takes to sink in. If we start with a model, there are things you can do and things that you can't in terms of working across these 3 scales. So if we're talking about predicted outcomes in logits, that's this mu thing, the result of what this model builds for us. I can take that in logits and unlogit it down to odds, and then I can further convert it down to probability. So this whole column is eligible. Question, the previous slide, are mu and upsilon related? Let's see. This is mu. Where is epsilon? Oh, yeah, I think I just typed it differently. Like it changed the font for whatever reason when I put a hat on it. So I may have, that may be a typo, or I'll double check it. But yeah, that I didn't mean those to be 2 different things. It's just that some authors put hats on everything that means to be predicted, and some just are like, it's assumed, you don't have to put it on there. So I was trying to make that there. So thanks for pointing that out. I had not noticed that the U looks different. I think I just screwed it up, but I will fix that. Eagle eyes. Very good. Okay, so that thing, whatever you want to call it, I can take a predicted logit, I can turn it into predicted odds by exponentiating it, and then I can take it 1 step further into predicted probability, and all of that is cool. So you can always take your predicted logits and turn them into other metrics. And that's what I would recommend to make sure people know what you're talking about, because people understand predicted probabilities, they don't understand predicted logits. For the slopes, though, those can only be taken down to the odds level. So if I have a slope in logits, then I can turn that into something called an odds ratio, which is indeed going to be a ratio of 2 odds. That is going to be an effect size for the slopes. So how the odds changes for one level of a predictor versus another. So we'll see that literally as like a stack of fractions in one of the slides here. But what we can't do is talk about the slopes in terms of what they do to probability. It does not work, because a 1 unit change in logit has a different corresponding change in probability depending on where you are on the curve. It's the biggest in the middle, and it shrinks as you go to the boundaries. So that's the biggest mistake that I see folks make when they're first getting into this. You cannot talk about slopes in terms of changes in probability. Cannot. So the order of operations then is we use the slopes to build a predicted logit. We then take that predicted logit and convert it into predicted odds or predicted probabilities. We don't touch the slopes in terms of probability. If you want to talk about effect size, then you can convert them into something called an odds ratio. Question? Yeah.
Yeah. Not talking about an exact value, but could you say, um, if the odds, if the B sub one, beta sub one is positive or negative, that it is positive means that it's like increasing, not a particular amount, but just in general increasing, and a negative is in general decreasing.
So
Could
with
you think
respect,
about it that way?
yes, with
With
respect to
respect, with
logits,
respect to the, yes,
to
or
logits. Yes, so if you have a positive slope, it means as x goes up, logit y goes up. If you have a negative slope, that means as x goes up, logit y goes down. That holds the same. Odds ratios, though, what happens is that, and this is in slides somewhere, but I'll just say it since we're on the topic, a positive slope translates into an odds between 1 and positive infinity. A negative slope translates to an odds ratio between 1 and 0. And odds have a lower bound of 0. You will never see negative odds. So that also makes this tricky because when you look at the numbers, if you're looking for signs to tell you what happened, odds ratios are always positive. So you have to really pay attention to the value and say, is it between 0 and 1? Because that means negative. 1 means a slope of 0, and a positive above 1 means a positive slope. And they're per unit as well. Okay, and so E then. We talked about this a little bit. E has left the building. E is not going to be in any of my equations like this entire semester until we get back to normal land, because E is a representation of the idea that the model has an estimated variance of the residuals as one of its parameters. We don't have that. It's because we know, based on what the predicted logit is, what the predicted probability is, and then we know what the predicted variance is right around it. So when you see an E, occasionally it might be because they're writing yet another version of this model, where they're referring to a pretend underlying continuous or latent distribution that gave rise to the 0 and 1 answers. This is a fiction. Y star is an imaginary thing. We do not have access to it. What the purpose of this is to provide a motivation for how we think about the metric that underlies logits, like what the scale is in terms of interpreting that. And the variance of these E things then is dictated by your link function. So in this world of it, we're saying, hey, Y star, this pretend imaginary thing is distributed as a logistic distribution. And the pink one in particular has a scale of 1 and a mean of 2. So the variance of the logistic distribution is pi squared over 3 as a constant, and that translates into 3.29. So you will see 3.29 show up in formulas to replace residual variance when we're talking about variance explained in logits. The problem is that 3.29 cannot be reduced after you add predictors that are supposed to have explained variance. It will stay 3.29. So the rest of the model will have to change scale as a result of that. Talk about that. But this is why. It's motivated by logistic. So then, is that the only choice? Someone said, do we pretend like the continuous underlying distribution is normal? You could. If you want to do that, then you have a different link function. Meet logit's friend, probit. And I don't know of another way to say probit. I don't think there's like log odds goes with logit. There's no like prob odds or something because odds are not part of the way it's made. So when I first saw this thing, I was like, yeah, what the hell does that mean? Like, this doesn't mean anything to me. I can explain it to you much more simply. Do you remember intro stat that you probably took as an undergrad or lower level graduate student? Some of you are teaching or TAing that right now. Like back in the day when you first get what's a mean, what's a variance, all that stuff. In your textbook, when you open up like the appendices, there's tables of distributions and critical values and probabilities and stuff. And there was one that had a mapping of Z as a standard normal distribution to probabilities. So you could look up the Z value and say, what's the probability for the area to the right or the area to the left? You could look at the probability and say, what's the corresponding Z score that goes with that probability? That's what probit is. Probit is the z-score that goes with the probability from that table. It is, more formally, the z-value that corresponds to the location on a standard normal distribution below. So it's the z-score that goes with the area to the left. That's what probit is. So it is also a continuous underlying idea. Rather than saying that we have logits as this continuous metric that's unbounded that we can predict, probits will do the same thing because z-scores go on forever and ever. And the neutral point in probits, z-scores, still 0. So logits and probits are both continuous symmetric distributions where 0 corresponds to a probability of 50-50. The same Bernoulli distribution is used for the zeros and ones because that's what we actually have in reality. We do not have anything continuous. We have zeros and ones. But if we say, well, what if we think about predicting the probit as this y star thing, then what we're saying is that, well, because probit is based on the standard normal idea, now the E star variance is 1, whereas the logistic variance of the E stars was 3.29. So there's a different scale that the model is on if you pick a probit link versus a logit link. However, should you care? No. You can get from one to the other. So this picture on the left here on slide 17, I stole this a long time ago. I couldn't find the original source, but I'm pretty sure I stole it from Don Hedeker, so thank you, Don. I steal a lot of things from him. He's a very brilliant person and very nice. So this picture overlays the logistic distribution with dotted lines here and the normal distribution with solid lines. So the difference is what the variance is of the pretend underlying distribution we don't actually have. Probit says it's 1 and logit says it's 3.29. It turns out some genius figured out that there's a rescaling constant of 1.701, if you want to be very specific, by which you can multiply probit by 1.7 and turn it into logit. It's just a rescaling. So once you do that, then the predicted probabilities, do you see the difference between the red and black lines here? Anybody? Any eagle eyes in the room? Do you see the difference? Yeah, a little challenging. Like maybe this, like just tiny little bit, like third decimal place differences here. So once you do the rescaling, they're on the same, they map. So they are two different ways of thinking about a pretend underlying distribution that our intercepts and slopes can predict. But if we back translate through inverse link, we end up with predicted probabilities that stay between 0 and 1. Same as logits. So they accomplish the same thing. Other things that I want you to know about probit, if you take item response theory, so that is latent variable models to predict categorical outcomes like this, probit is known as ogive. Probit does not have odds ratios because it's not built from odds at all. So we skip that entire middle layer when we talk about probits. And I would not talk about this at all, except that later on, if you have very complicated models predicting categorical data that are estimated with sort of a shortcut known as limited information, that means you're summarizing the data first and then feeding that summary into the model for it to work on instead of the raw data. Probit is the only choice in those kinds of models. So you're going to have to see it at some point if you keep going anyway. Ogive is cumulative probability. It depends on how it's phrased, but in this context, no, it's just area to the left. So it's like the probit, what is being predicted is the z-score that would correspond to that spot on the normal distribution. And these both assume symmetry of the curve, but there are other options that don't. Yeah, cumulative to the left. So I think someone asked this question maybe last week or maybe Tuesday, but are there links that are asymmetric? And yes, there are. So I just want you to know that these exist, okay? Can we agree to that? Just that's the point of the slide, just know that they exist. So I have here 4 different choices. Blue and purple, which are pretty much indistinguishable, is logit or probit rescaled to match logit. So probit times 1.7 is logit. Now they both rise away from a probability of 0.5 at the same rate that they decline away from a probability of 0.5. So it's a symmetric kind of curve here. The other ones, red and green, are for skewed data, instances in which there's a lot more ones or a lot more zeros. And this is the one that I will never ever remember. Log is the name of a link function in which ones are more frequent. So the red line here, if you have a lot of ones in your data, then the probability between 0.5 and 1 is relatively more well predicted than the probability between 0.5 and 0. So this link function sort of de-emphasizes the 0 side so that it can focus more on the 1 side. And the green one is the opposite. So then it emphasizes the 0 side and kind of lets the 1 side trail off. So how these link functions are built is right here, the inverse link to get back to probability out of these here. And the pretend underlying continuous distribution that goes with these is known as log Weibull or extreme value or Gumbel. And I have a Wikipedia entry here, and it's pi squared over 6 for its variance instead. So if you have a binary variable that is heavily skewed one way or the other, these alternative links could be a better choice for you. You can, essentially it's an empirical question. You can use something called information criteria to find out. So probit and logit are symmetric link functions. The other two are asymmetric. All right, questions or comments right now? Pi is referring to the symbol, not 3.14. No, it is 3.14. It's pi squared over 6 instead of over 3, but it is pi as we know it.
Lisa, can you review again the logic behind why Probit has the same variation for every model?
Yes. So probit is a different scale of the underlying variable that's continuous that we're trying to predict. So the job of a link function is to translate predicted probability, in this case, into something that's continuous. If you think that the continuous thing is a logistic distribution, that goes with logit. If you think the continuous thing is a normal distribution, that goes with probit. But they are imaginary. Like they're motivating distributions for what could have happened to give rise to our actual zeros and ones. And so the difference between these is just a matter of rescaling one to match the other. So if you don't do any rescaling, if you take your predicted logits and you turn them into probabilities, and then you rerun your model with a probit link, and you turn those into predicted probabilities, the probabilities will match. It does the same thing, just with a different scaling. But if you look at the coefficients, like the slopes, they will be off by a factor of 1.7.
Okay, thank you so much. And that actually, I asked the wrong question because I said probit,
Okay.
but what I meant was logit. Like I understand how probit and logit relate, but I think I'm still stuck on like why is variation the same for logit every time you run the model? Why is it always 3.929?
2.3, yeah, 3.29 or 1. Because variance isn't estimated, so it can't go down. Like it's a fictitious idea because we don't know we don't have the underlying data. Like if we truly had continuous data that followed a normal or logistic distribution, we could estimate either a variance in a normal or that scale factor thing that kind of functions similarly in logistic, but we don't have it. So we can't reduce it because we don't have access to it in reality.
Why isn't variance just 0?
It's not 0 because our model is not perfect.
Mhm.
So E as a concept of being how wrong the model is for predicting your outcome is still there. But it disappears from the equations because once we know what your predicted probability is, we know how wrong it can be. This much wrong to go up to 1 or this much wrong to get down to 0. And so we know what the variance has to be at that point. And it's not the same number. So that like in terms of what the residual variance is, it's different for people with a predicted probability of 0.9 than people with a predicted probability of 0.5.
So, okay, I'm still confused.
It is confusing.
I'll read more.
Yeah, the numbers don't really mean anything in the way that we're used to thinking about it because we don't have access to them. They're just sort of like reasons for doing this. Yeah. There is no such thing as R-square in these models because of these reasons. And so people have used these kinds of ideas to try to justify ways of forming an R-square. But there's literally dozens of them and they don't agree. But in many of those formulas, you will see 3.29 like stuck in there. And that's why I want you to like, oh, that's where this is coming from, is because we're assuming we're talking about the variance explained in logits or in probits, which we don't have access to. Can I give you a Coles analogy? I haven't had one of those this week, I don't think, so it's time. So what happens in practice is that the model changes scale. It increases in scale as you explain variance. So if you fit an empty model in logits, the variance is 3.29 because that's what logit says it is. If you add the world's best predictors, the variance is still 3.29. And if you're in probits, the variance is 1. You add the world's best predictors, the variance is still 1. But the rest of the model in terms of what y is has more variance to it because the E part stays fixed at 3.29, but the linear predictor introduces new variance. So where Coles comes in. As I said before, if you pay full price at Coles, you're doing it wrong. Everything is always on sale. So let's say that I'm the manager of Coles and I have a pile of ugly sweaters that I need to offload, but they're kind of expensive and nobody wants to buy them. Let's say that to make like ends meet, I need to get at least $25 for each of these sweaters. So what do? I put a sign up that says the sweater costs $50, but it's 50% off. And then I unload some of the sweaters. And then the ones that are left, I'm like, well, now regular price is $100 and the sale is 75% off. And it's still $25 at the cash register. So the model is essentially trying to work with what the regular price would had to have been for you to still get down to this much variance left over as a fixed number. So as you explain more variance, which you can't see, the slopes will get bigger and bigger and bigger because they're targeting what the original price variance would have had to have been. Apparently I need a new sweater. I have strings hanging off of mine. I think this shirt actually came from Penny's, if I remember correctly. Oh no, this is Costco. Been pleasantly surprised by Costco clothes. Just, they run big. That's my only tip. There we go, problem solved. Variance is fixed, so something has to give to make the prediction. The scale of the model changes because that's the way that I would think of it. Nothing is going to give, so you had to pretend that there used to be more variance in y to begin with in order for there to still be left over 3.29.
Wow.
So from a practical perspective, I think you can ignore most of this. What people tend to do in practice is provide an effect size per slope that is called an odds ratio, which I'll show you in just a few slides, I think. And you can report an R-square if you want to, but you'd have to be very specific as to which one and be prepared to defend that choice because you don't have the original logits to see how much variance you reduced. It's a nonlinear transformation that is trying to map onto data you don't have that are continuous. I'm not making it better, I don't think. I'm trying though.
I mean, I really appreciate all of your attempts. I think my brain is stuck on this, so I'll watch this part of the video again and read what I can and come to office hours if I can't.
Fair enough. Fair enough. Vladimir, do you have anything to make it better?
I think that I would say that the thing is when you are analyzing data, let's say that you have an outcome you're interested in is binary, and you must make a decision about how to analyze that data. And binary is not the same as dichotomous. I was thinking about it. I don't know if in R, for example, you can use, let's say, ones and twos instead of zeros or ones. I don't know, but we are always working with zeros and ones because that's binary. But I don't know if one and twos are the same thing because you should pay attention to that too. But the thing is, we have our binary outcome. We must make a decision about how to analyze that thing. We have a set of predictors. That decision about how to analyze that variable depends on what you want to do and what's your area, for example. For us, the logistic function, the logistic link function is like the normal option. I would do immediately a binary logistic regression. But I've seen that for other people in educational measurement, they like Probit. So they go with that version. But at the end, the conclusions will be the same. They will overlap because you are not transforming your data. You are just making a decision about how to go with the model scale. So I hope that helps, because at the end you will have your binary outcome and you must make a decision about what the model scale will be, logit or Probit. Now, if you have more zeros than ones or more ones than zeros, you will need the C log log or the log log. So, but those are decisions. At the end, you will have the same conclusion regardless of what model scale or link function you are using. I hope that helped.
Yeah, you just have to kind of know what your scale is, because then it makes it easier to know when you can and can't compare things. Like if someone runs a model in Probits and someone else runs a model in Logits, the values you get back on your output will be different, but they're different by a factor of 1.7. And when you translate the predicted outcomes into Logits or Probits down to probability, they will match. So it doesn't really matter as long as you're picking like from two symmetric link functions. It's just within each of those, as you add predictors, the model scale of what the total variance would have been has to increase because the residual part is fixed. And with respect to binary versus dichotomous, yeah, R will either yell at you that you don't have zeros and ones, or it will just like work with it. I know that with ordinal data, you can start at not zero and it will be fine. So I think it just does it in an ordered fashion. It doesn't necessarily pay attention to the values, but I could be wrong on that. Okay with the difference between Probit and Logit, having trouble with why we estimate a variance even though we have no way to know what it is. We're not estimating it. That's the whole thing. It's fixed. It is fixed to this known value based on this underlying distribution that we are pretending is there but we don't have. See, and you thought statistics was boring. We're engaging in like creative writing at this point. This is fiction class right now. That's what I call power analyses, by the way, creative writing. That's a topic for another day. All right, so asymmetric logs. Here's one more thing that I want to put here because it's going to show up in ordinal. The idea of something called a threshold replacing an intercept. And this has to do with which way is up, which is what we tackled last Tuesday in trying to figure out whether our model is predicting the 0 or the 1. So some people explain these same models by referring to this pretend underlying distribution. So this one is a normal one that I stole. And so this would be like in Probits. And they would say, let's say hypothetically that this is the point at which 0 switches to 1. And I know that because I can figure out, like when I estimate the model, what it gives me. And so some software packages use this version instead, which is called a threshold. This idea, it's literally like the cut point, like where does the response switch? So there's an intuitiveness to it. However, if you look at the number here, the number is -1 on a standard normal distribution. That corresponds to a probability of 0.16. So it's actually talking about the probability of a 0 instead of a 1. So thresholds and intercepts are logically backwards things from each other. You have to multiply them by -1 to get from one to the other. So some software will spit out intercepts, which gives you the probability of a 1. Some software, like M+, will spit out thresholds, which gives you the probability of a 0. But this is why it might go the wrong way, is because it's approaching it from this kind of perspective. In this unit, in talking about binary, I'm going to avoid this problem, but it will be unavoidable in ordinal data, and I will show you a way to make the software do what we want to get intercepts instead. Okay, one other new thing. So residual variance is gone because we don't have a normal distribution with a separately estimated constant variance. And denominator degrees of freedom are gone. Sums of squares are gone. All that stuff is gone. We're in likelihood land. So most software for generalized models does not use denominator degrees of freedom in doing hypothesis tests. So what you get then is going to look a little bit different. If you're testing one slope, estimate divided by standard error is now going to be used as a z in terms of the reference distribution that you get your p-value from. If you are testing more than one slope, then it's going to be chi-square instead. Whereas previously in linear models land for regular regression, we had t's and f's. So this means in practice that if you don't have a very large sample, that these distributions are not going to be appropriate in the same way that we needed t in the first place because z was not working for very small samples. And these results can further differ across programs as a consequence of how they compute standard errors. So we're going to look at different things than usual to decide if something is significant and if something helps the model. And as a replacement for like the overall f-test for the model, we're going to compare heights of alternative models. So remember log likelihood, that idea? How tall does the model make your data? Given the distribution that we're working with, calculate the likelihood, take the log of it, sum across people as independent. The sum of that is log likelihood as a number that says how tall your data are collectively under this model. So we're going to collect these of alternative models and compare them. So we have maximum likelihood in this class. There's another variant of it that shows up in coursework and mixed models, but you won't see that this semester. What you get on your software, though, is different. Some software spits out log likelihood, which is height, and some software multiplies it by -2. The reason for that is that while the absolute amount of log likelihood doesn't have any meaning, like it could be -275 and we don't know what to do with that in absolute, the difference between log likelihoods is distributed as a chi-square if you multiply it by -2. So that's where that comes from, is because they know that to compare how well a model predicts something against an alternative model, you're going to have to multiply each of the log likelihoods times -2 anyway, so they do that for you when printing it. So either version of the formula, we have -2 log likelihood as given directly for the model that has fewer parameters minus the one that has more, or if you get log likelihood, you can still take the difference in the same direction and multiply that by -2. Then that is a test statistic that you will then compare to a reference distribution, get yourself a p-value. So likelihood ratio test is the name of this. It's subtraction when we're dealing with logs. It would be division if we were dealing with original likelihoods, but that's almost never going to be the case. So the rules for this test then, you end up with a comparison. Did the data get taller under the new model than the old one? That's the question. So if you run this test and the result is significant, your test statistic, your chi-square, it has exceeds the critical value, then you would say that your model got better. If your critical value is not exceeded, if the result is non-significant, then you would say the model is not better. You added things, but they didn't help. And you would use the opposite terminology if you were comparing, starting with a complex model and trying to simplify. If you do a comparison from that perspective and it's significant, you made the model worse by trying to simplify, as opposed to not worse if it wasn't. And there's other things too that I'm not going to use much this semester, but you may see them. Information criteria are transformations of log likelihood, where they penalize it for number of parameters estimated. So these are like accompanying numbers that you'll see on your output sometimes. They don't have any critical values or distributions, just smaller is better for those. And because I thought this is probably a lot of a refresher here, I made some pictures. Right? And by made, I mean I stole. So this is chi-square. This one was stolen from Wikipedia here. So K is the number of degrees of freedom. For our purposes, that would be the number of terms that you've added to your new model to try to make it better. So if I add one new predictor and I want to do a test to see if that improved my model, then I follow this yellow distribution, and where 0.05 starts in terms of the area that remains, where 5% the boundary is for that test, is at 3.84. That's the critical value at alpha 0.05. Terms beyond beta 0. Yes, any new slopes, any new interactions, anything that you're adding to the model to try to help it. If I add two things, then that follows the green distribution here, and the critical value is 5.99. I ran out of room, but I know 3 is 7.82, 4 is 9.49, and after that I don't have it memorized. So what the shape of this looks like depends on how many things you've added. This isn't something you need to memorize or care about because you'll get an exact p-value for it. I just wanted to sort of remind you that you've seen chi-squares before because they're used for other things. Then we have a comparison of t versus z in terms of testing just one slope. And so z is the black line here. T distributions for smaller samples would be a lot flatter. There's more area on the end, and so the critical values have to shift out to get to where 0.05 starts. So we're used to dealing with t's, in which you need to know what your degrees of freedom are for the denominator, number of subjects minus number of parameters spent. We're not doing that anymore because we're just using z. And then we have f, which is the multiple slope version of t, which is going to be replaced by chi-square. And so f has two components to its degrees of freedom, numerator and denominator. And I found this picture which illustrates the difference. So let's say that we add 8 slopes to our model. The f distribution, if we had 40 remaining denominator degrees of freedom, would be the taller one. And if we only had 4, which would be a very small sample, it would be the shorter one. So in terms of where 0.05 starts, it would be here for the larger sample, and it would be clear out here for the other one, because there's going to be a lot more area that's left over there. And then here's another comparison of these as well. So point of the story, estimate divided by standard error, we used to call t, now it's z. That means that in smaller samples, it's going to have a little bit high type 1 error rates because we're too far in terms of where 5% starts. The same thing happens with respect to chi-square versus f, but that's not something we can control. So you're going to get used to seeing z's and chi-squares on your output instead of t's and f's is the point of the story. Now odds ratios, this thing. This is our measure of effect size, and it's going to be used pretty much throughout the semester. Most models are going to have some version of this. So if I have a model that looks like this, on the y side here is logits, the log of the odds of the probability of a 1. The right side here is my linear predictor. So I'm interested in getting effect sizes for beta 1, which is the slope of a pretend binary x, and for beta 2, which is the slope of a pretend continuous c. So for x, the odds ratio for that slope in logits is computed as e to the slope. That works out to be this thing. So the numerator of this giant thing covers what the probability of a 1 versus 0 is in the case in which x is 1. The denominator covers the same thing in the case in which x is 0. So as stated earlier, this is a ratio of odds. There's an odds given x of 1 on the numerator, and then what are the odds given x of 0 in the denominator? So we have two sets of odds being divided into each other, an odds ratio. The same idea holds for a continuous predictor's slope, but then it's just like a 1 unit change. So it would be like the numerator is 1 unit apart from the denominator with respect to what x is, and you'd have to decide what to hold other things constant at to be able to figure out the probabilities. So here's why I don't like this. I actually have multiple reasons, but here's the biggest one. The odds ratio metric is asymmetric. It goes from 0 to positive infinity. So if I have a slope of 1 in logits, e to the slope in logits is 2.72. What that means is that the odds of a 1 are 2.72 times greater per unit of x. And so I made a little table here to show how this works out in terms of the numbers. So if I have a slope of 1 and I go from a predicted logit of from 0 to 1, that translates into odds of 2.72. If I then multiply that by 2.72, I get to this one. Multiply it again, I get to this one. Multiply it again, I get to this one. So for every unit of x, the odds increase by a factor of 2.72. It's multiplying together. So predicted logits look like this, predicted odds look like that. Now the converse, a slope of -1 in logits. Now can we agree, just looking at these numbers here, that a negative slope of 1 is just as strong in terms of conveying a relationship as a positive slope of 1. Can we agree on that? Okay. Positive means as x goes up, y goes up. Negative means as x goes up, y goes down. Well, now if I compute the odds ratio, it's 0.37. And so then going backwards, my odds are diminished by this factor of 0.37. So to me, this is weird in the sense that positive slopes get to have all of the range from 1 to positive infinity to express themselves, whereas negative slopes are shoved into the range between 0 and 1. So it just looks like it's a lot smaller of an effect. It's harder for me, I feel like, to judge the relative sizes when they're in such different metrics of what a positive slope can be and what a negative slope can be. So I don't find this useful, but if you work in medicine or certain fields where categorical outcomes are predominant, like sociology, for instance, odds ratios are the game in town. Like, this is something you'll be expected to provide. So I will show you how to get them out of Stata and out of R with a minimal level of effort. The programs have this command built in. Okay, questions on any of that? Are you still with me, Zoomers? You're awful quiet today. Oh, there's some thumbs. That's reassuring. I know it's a
Are
lot.
the products, as I say, are the products of the corresponding number of 2.72s in this example and the 0.37s that you are multiplying, if you multiply those together, like 2.72 times 0.37, is that going to be the same as 7.39 times 0.14? Because they're kind of going in opposite directions, not exactly, but
No,
is that
each
going to
one.
be constant?
No, each one is constant within it. So like if I take the first one and multiply it by 2.72, I get to 7. 7 times 2.72 gets me to 20. But then, and the same pattern works here, but it's this multiplier instead of that one. I don't know if that helped or not.
Well, that's not what I'm thinking. I
Okay.
don't want to waste class time on my thought. That's fine.
Okay, well, you can ask me afterwards. So the other reason that I don't like odds ratios is because they're supposed to be effect sizes, right? That's the idea. An effect size is on a metric that you immediately know what it means, and like a D, you know, is a standardized mean difference in terms of standardized units, or an R or an eta metric, you know, should range between -1 and 1, and you have a sense as to like what that should be. Odds ratios still are in units. So if I have a variable as a predictor that's binary, a 1 unit change is the entire length of that variable's possibility. You can only be a 0 or a 1. So a 1 unit change covers the entire distribution of my predictor. Whereas if I have a continuous predictor like a scale score, a 1 unit change is 1 increment on that overall scale, not the whole range. So then you end up with what looks to be smaller effects because one has a unit that is the entire scale of the predictor and the other is just a small increment in it. And that's a problem that hasn't really been solved to the best of my knowledge. Like, it's not a true effect size in the sense of being comparable across different kinds of predictors. It's only comparable within the same kinds of predictors. And Vladimir is going to do a presentation maybe next week. I think probably Thursday is what I'm guessing here. Showing an example of how he used logistic regression in a project, and he ran into the same sorts of things because you have these like binary predictors for, you know, your income class or your gender or whether your parents are this level of degree or whatever, but then you have things like test scores. And so a test score has many, many units to it, and moving up 1 would generate a very small odds ratio in comparison to moving from a 0 group to a 1 group in some other predictor. So I find these dissatisfying for that reason as well. But that's just me. Okay, so trying to recap then in terms of what you can and can't do. Odds ratios are what we're going to use to talk about slope effect size because that's what the world uses, but we are not going to use slopes or odds ratios to talk about changes in probability. It's not going to work. All right, R square then. We're getting very close to, we're getting very close to seeing some more stuff here. Correlations, in fact. So R square is gone. There are things called pseudo R square. Here is a list. I'm going to show you a list in your output as well of all the different kinds. The one that Stata provides by default is this one. It uses log likelihood as the basis of R-square, where you have the one for the current model relative to the one for the empty model, and then 1 minus that gives you R-square. And there are many, many variants. So I'm not going to make too much use of these because I don't know that this is useful information. There are other variants that people have proposed that make use of these distributions, and this is the one that I was hinting at earlier in talking about Coles. Like we have the variance of the predicted values in the numerator, and then the total variance is those plus the variance of these pretend residuals that is fixed at this constant. So when you add predictors and spread out the range of predicted values, you're increasing the total variance. So then you have that in the numerator as what is the range of prediction relative to that plus the error that's fixed. So this one I've seen in other contexts as well. It seems to make a little more sense to me, but still not something that I just want you to have seen it, not really paid too much attention to it. Okay, correlations. That's what I wanted to get to. Who remembers what a correlation is? Let's leave Logit land for a minute. What's a correlation? Softball question. No one remembers. Or you're shell shocked. Strike one. It's not a trick, I swear. What's a correlation?
How well it fits?
How well, I would say how well it predicts, maybe.
How well it predicts. Fair enough.
Yeah.
Like a high correlation is good.
Yes. So correlation is how well X and Y go together. Like if you're above the mean on X, are you also above the mean on Y or below the mean? Yeah, it's a measure of association. And have you been taught about kinds of correlation before? A few of you have. The square root of a regression for a bivariate GLM? Yeah, you can say that. I think so. So Pearson correlation is probably the one that you're thinking of because that's like the default. When people say correlation, that's what they mean. You may have also heard of Spearman correlation. That's when you take your data, convert it into a rank order data set, and then run Pearson on it. We're not going to do that one. But there's other kinds. And the point of this story is that a Pearson correlation is not a good measure of association for binary outcomes. Here is why. Remember that we have variance that is determined by the mean. So the variance of a binary variable is the proportion of ones times the proportion of zeros. Okay. So that means that if the two variables differ in their proportion of ones, that is going to necessarily limit how related they can be because it limits the variance, and if you have less variance, you have less chance to show covariance. So here's a formula by which you can anticipate what the maximum correlation between two variables could possibly be if they don't have equal distributions. So it's quite a bit less in some cases. So look at this one here. If one variable has a mean of 0.1, so 10% of the people got a 1, and it's trying to be correlated with the variable where 80% of the people got a 1, the maximum possible Pearson correlation you can have is 0.17, not 1. And you can look through this list here and see just how extreme that this gets based on these things. So you end up with essentially a range restriction problem showing up in your Pearson correlation. So I want to give you what to do instead. So here's correlation. I stole some pictures from when I reviewed this in intermediate. This may look familiar. So if I have a scatter plot of X and Y, a perfect correlation of 1 would be a slope like this where all the dots are on the line. As the dots sort of fall off the line, that would indicate a correlation that ranges between 1 and 0. 0 would be just like a circle, no pattern here. The best fit line would be flat through the points. And then you can start heading in the negative direction where you have, getting closer and closer to this line here. Okay, remember this much. Does that work? Okay. Now we can use this idea to try to anticipate what the correlation would be in binary data, wait for it, if we had the pretend underlying continuous distributions that don't exist. We're going to correlate them. And this sounds nuts when I explain it that way, but I can make it sound moderately less nuts by showing you a couple pictures. So what we have in reality for two binary outcomes is a contingency table. Cell A is for people who had zeros on both. Cell D is for people who had ones on both. And then the other cells are for people that have disagreements, essentially. Well, I know what the proportions are in each of these 4 cells from my data. Now, if you think about what that would look like in terms of the correlations down here, a perfect positive relationship would mean that everybody is in cell A or D. Right? If I got a 0 on one, I get a 0 on the other. If I got a 1 on one, I get a 1 on the other. A perfect negative correlation means everybody would be in C and B. And a 0 correlation would mean that it's like split evenly across the 4. So if we know this much, then we can kind of hack that into thinking about, well, what if we actually had this bivariate normal, like 2 variables at a time, pretend underlying continuous distribution? Then we can figure out, based on the proportion of people that would have been in each quadrant, what the underlying variables correlation would have been that created these observed proportions in each of these cells. That is the basis of something called a tetrachoric correlation, which is what we're going to use for binary data. So it's a different way of computing a correlation than what Pearson does. It's not something you can compute by hand very readily, but it's something you can compute with likelihood, right, Vladimir? I know you had to do this as a homework in Jonathan's class, right? He made you guys do this. Yeah, see, look how nice I am by comparison. I don't make you write likelihood functions. Was it challenging?
Yes, in fact, was Alfonso and Mubarak the persons who solved that. I was there in the meeting because we were studying, and I was like, wow, that's magic, guys. Couldn't do it, but I understood the machinery behind tetrachoric and polychoric correlations.
Yes. Is this also called Youdin's J or B index? I have no idea. I've never heard of those things. Possibly. I know there's many, many measures of association for categorical data, and this is one, but this one shows up in structural equation models that involve binary outcomes. So this is one that you'll see again. 2 terms are synonyms used to compare the number of false alarms and true hits. That probably is a different animal then, because then that's referent to some kind of expected, like what you would get from chance kind of performance thing. So this is not correcting for chance per se as a measure of association. But it's based on this idea, like what is the shape that would had to have happened for the cells to be distributed in the way that they are. That's what it tries to figure out, what the correlation would be consistent with that. So trying to, hang on, where'd my slide go? I was missing one. Hang on, maybe I skipped it. Yeah, I think I deliberately skipped it because I thought this is enough. Sounds like sensitivity and specificity to me. Okay, now we are at the point where we can go back to numbers, because I know you like numbers. You like it better anyway. How about we look at some descriptives and correlations, since we just talked about that. Let's see. Yeah, okay, so those are different animals then, in a sense, what we look at. So we're back in example 2. These are data, again, predicting whether or not someone is likely to apply to graduate school as the 1 and absolutely not as the 0. In this particular simulated sample, we know that 45% of the people have a 1, which means 55% have a 0. So the first thing that one would typically report in any kind of regression type analysis would be how related the predictors are to each other, as well as to the outcome. Get that out of the way. So we're going to do that, and I'll show you the difference in what happens as a function of these kinds of correlations. So first off, the regular kind. So in Stata, there is a command called pwcore. That stands for pairwise correlation. That one is preferred if you have missing data, because then it estimates the correlation between each pair using all the cases that have both, whereas the standard core drops out anybody who's missing anything. So this will keep more of your data if you have some missing data. So you list out the variables that you want. So I have whether or not they're going to apply, whether or not a parent had a graduate degree, whether or not someone went to private college, and then their GPA centered at 3. So if we look at the relationships here, it looks like there is a positive correlation between the likelihood of wanting to go to graduate school, and whether someone had a parent who went to graduate school. No surprise there. Private school looks to be mostly unrelated, and GPA is also slightly related as well. There is an easy function in base R, just COR for correlation. So what I had done to this is subset the data to just these 4 variables so that I could feed in the entire data set and run in a correlation. Does apply to in this case have to be listed first? No, these are not predictors and outcomes. These are just variables that I'm looking at a correlation for. And the same is true in R here. So we would agree that these are not super strong relationships, right? A correlation of 0.2, it's significant, but it's not very predictive. Now, if we go to a different command, this is a user-created command that is known as polyquark. That's what it's called when you have ordinal variables, in fact, it says instead of tetraquark. So I had to download this and install it. It is something that someone wrote to be able to do this. And lo and behold, look at the differences. So the correlation between applying to graduate school and having a parent that went to graduate school is now 0.38. It used to be 0.2. So it's literally twice as big. The rest of these also changed in terms of being stronger in the tetraquark version of the thing. So it does make a difference what your measure of association is. And if you're working with correlations among binary variables, this is the one that you would prefer. There. My mouse keeps moving. Darn it. Okay. 309. How are we doing, folks? Okay-ish? Thumb sideways. Thumb sideways is the best I'm hoping for right now. All right, so it looks like we will need most of the next class to finish up this handout and to make sure that everything has sunk in well enough. Yeah, gritted teeth thing. I think that's a good thumb sideways one. And so I'm going to push your first homework back 2 days to Wednesday. That way you have at least a full week to work on it. Question?
So if Pearson correlations are really affected by the range of the data, are they best used for outcomes that are unbounded?
Yes.
Polyquark correlations are used for outcomes that are bounded but have a range. And then tetraquark is best for things that are binary.
Yes, tetraquark is best for binary. The same idea, but extended into a bigger contingency table in terms of where the area is and what the correlation would have been. That's polyquark. And yes, that is for ordinal data. But Pearson correlation is the idea of continuous variables. It maps onto the idea of a bivariate normal distribution that is truly uncontinuous.
Time I was rating a sample of tests with another person, and then in that one particular sample, it was a rating scale from 1 to 5. We had almost entirely all 4s and 5s. And we had like almost perfect agreement, like exact agreement on almost everything. But we had like 1 or 2 things where we were 1 level off from each other. And our agreement was like 0 because like we had gone this way and we had gone this way. But then we added in another stack of samples, and there was one sample there where the student had done very badly and both of us gave them a 1. And suddenly our agreement jumped up to like 0.98 or something crazy like that because we had more range in our data. We were just using Pearson at the time. Like that example helped me to see that Pearson is really sensitive to like the range of the data. And if you just have some little scores right next to each other, it's not going to be very sensitive in like understanding how well you agree.
I agree. And I think for that case, Cohen's kappa would probably be a better choice for inter-rater agreement, because then you're trying to work out like what is sort of the base rate based on how many 4s and 5s there are. Because like if most of the data is on one side, you're going to agree just because of that. And so I think that like that's a problem that folks have worked on in terms of inter-rater reliability. But this would be an alternative potentially if you truly have binary or ordinal ratings.
We use Cohen's kappa now because of this issue. Yeah.
Yeah, so this is the slide that I was looking for and I forgot that I moved it. But since y'all are asking great questions now, here it is. This is slide 39. So in terms of correlation names, these three are identical. Pearson, phi or phi, however you want to say that, and point biserial are the same damn thing. The latter two have special names that arose out of computational shortcuts when people used to have to make this stuff by hand. But they are based on the same thing because they are based on means, variances, and covariances, assuming the variables are continuous. The line of suspended disbelief then gives us the next three. So tetrachoric is kind of like the correlation of the probits. That's not accurate, but I think it's accurate enough to hang on to. It's for two binary variables. Polychoric is ordinal with ordinal. And then you end up with bi or poly with serial after it if one of them is continuous and one of them is binary or ordinal. And the software that I found in both Stata and R automatically figures out which one you need based on what kind of data you have. It's glorious. And it puts it all into one nice correlation matrix and tells you what kind it is. Yes, it's lovely. So I found this the last time I taught this class, and I was very excited to bring it back. But these are measures of association that would work better in categorical data is the point take home. So in the same way that we need to change the regression model because we have boundaries and binaries, we got to change the correlations that go with it. Same problem. Okay, did I get all the questions? Polychoric is ordinal with ordinal. All right, anything else before we wrap up for the week? Then thanks for being here. I'll hang out for a minute if anyone wants to talk to me. Otherwise, work on your next bridge activity. We'll do that in class on Tuesday, and have good weekends. Stay safe and warm. Bye for now.